Welcome back, chemistry fans. Today, what we are going to do is part 2 of our Unit 9, Topic 3, about gas laws. We're going to continue to build on the ideal gas law, but now we're going to change something. It's fundamental to this that we got to understand that the ideal gas law had one set of conditions. So what happens if we change the temperature? If you have a gas trapped inside of a balloon and you heat it up, it's going to expand. Or if you cool it off, it's going to contract. And that's all a matter of the kinetic theory. We talked about this earlier. We built this case that as you heat up, you cause there to be more energy, they move faster, they get further apart. That's what happens, you expand the volume. So we got to account for that fact in the equation that we've already discussed, the ideal gas law. And so here it is whenever it shrinks. So what we're going to do is I'm going to set up the PV equals nRT, but I'm going to put ones on here. These are the initial sets of conditions. So imagine you have these balloons, and then twos will be the secondary conditions. Well, if they are in balloons, that means the gas is trapped. That means the amount inside the balloon does not change. So we can cancel those out as being the same. Well, by the very definition of what a constant is, it's not going to change. So we can cancel that out. So right away, I'm already left with a simpler equation. I've got P1 V1 equals T1. So I can rewrite this. P1 V1 equals T1. Over here, I'd have P2 V2 equals T2. Well, now I'm going to set up a comparison. So I want to set up a ratio. So what I'm going to do is I'm simply going to bring over the P2 V2 equals the T2. So all I'm doing is I'm setting up a ratio. That's all I'm doing. I'm comparing one set of conditions to another. We're just comparing. So what I got to do next is I'm going to simplify this a little bit. I want to get all of the ones and all of the twos on the same side. So what I'm going to do is I'm going to rearrange. I'm going to move these because it is a ratio. This is just a ratio, and this is just a form of cross multiplication. So what I can actually do is I can have that P1 V1 over P2 V2 equal to T1 over T2. I just rewrote it. I'm going to cross multiply. I'm going to switch those two positions. So I end up with now my final equation, P1 V1 over T1 equals P2 V2 over T2. Now I have my initial conditions versus what happens with my final conditions. And that's what this combined gas law equation is all about. Now, the reality is the ends don't matter because we will deal with that one separately if we need it. I want you to be able to look at this, though, and say that it is P1 V1 equals P1 V2. So if I change the number of moles, okay. But if not, we've got it. So let's try and use that very equation. Now, how do I know that I'm not just using PV equals nRT? Well, how I know is because I look at this and I see that there are two temperatures. I only have one temperature here, so that can't work. So instead, what I'm going to do is I'm not going to use PV equals nRT. I'm going to use PV over T equals PV over T. And this is P1s and these are P2s. All right, so now let's start substituting in. These are all my initial conditions because they all talk about it starting out here. So I've got 125 kilopascals. I've got a volume of 3.4, and I have a temperature of 297. On the other side, it says that I start off with a temperature of I end with a temperature of 310, and my pressure is 145. What I don't know is the new volume. So I'm just going to cross multiply 125 times 3.4 times 310. And then I'm going to cross multiply down here to get that V by itself. So I have this value divided by 297 divided by 145. and I end up with 3.05 liters as my answer. This is the combined gas law. So if I have this combined gas law and I want to solve for just one of those variables, well, I could rearrange it and solve for just one of those. And so that's what we've got now, is a scenario where if I don't have any temperatures, I can get rid of it. I can get rid of the temperatures. So remember what the equation was originally. It was P1 V1 over T1 equals P2 V2 over T2. Well, if there is no temperature change, you end up with just something called Boyle's law. And what we need to understand about Boyle's law, we did this as a lab last time, the more you increase pressure, the more you decrease the volume. They are inversely related. So their graph will look just like this, which is what your data will look like from the laboratory. Let's do a practice problem with this. Now, again, how do I know that I'm not dealing with PV equals nRT? Well, let's take a look and see. We start writing PV equals nRT, and I notice that I've got two temperatures. I'm sorry, I have standard temperature and pressure, which is 273 Kelvin and 1 atmosphere. Well, that means that I have 101 kilopascals. Hold on. I have two pressures here. This only has one pressure in it. So therefore, I need to establish PV over T equals PV over T. Now, there is no mention of two different temperatures. There's only one temperature. It says it's at 273. What I see is that it's asking for a volume and they give me a volume. So that means there's two volumes. That means there's two pressures. The temperature is not needed. So I end up with my equation PV equals PV. So what I'm going to do now is I am going to start with STP. I have a pressure of 101. It says that it increases 100 more, so that makes it 201. My volume says it's starting out at 3. I don't know what my new volume is. So let's plug this in. So I've got 303 equals 201 V2. So I've got 303 divided by 201, and I get 1.5 liters. Okay, that was called Boyle's law. Now, what if the pressure doesn't change? What if the pressure stays the same, but what happens is you increase the temperature, the volume is going to change. So what we're going to do now is we're going to put this into a new equation. We get rid of the P and we have Charles' law. V over T equals V over T. As you increase the volume, you increase the temperature. And so what we are going to have to deal is this equation in practice. So let's take a look at this example problem. So how do I know it's not PV equals nRT? Because I look at this and I've got two volumes. That tells me I'm going to be dealing with the combined gas law or some version of it. Now, I don't see any pressure mentioned. So we can get rid of pressure and I have V over T. So my first volume is 300. It says my first temperature is 305. My new volume is 447, but I don't know what my new temperature is. So that's what I'm solving for. So cross multiply 305 times 447 divided by 300. And I end up with 454.5 as my temperature in Kelvin. Well, there's one more way in which we could deal with these problems. But we're going to leave it right there for right now until I can fix that. So hang tight and I'll be right back. Okay, The third equation that we need to talk about today is Gay-Lussac. And now what's going to happen with his equation is that it is pressure over temperature. So the volume is going to be held constant in this case. So notice these canisters, they are the same size. It's not moving up and down. What is changing is the temperature, and that causes the particles to move faster. And so that causes more pressure. So here's how that works out as a graph. It is a direct relationship. Gay-Lussac says that as you increase pressure, you increase temperature. All right, let's practice one of these problems. And so in this one, how do I know that I'm working with Gay-Lussac? Well, I noticed that there are, whoops, this one is Avogadro. So let me go find Gay-Lussac's problem. Volume and temperature. I need pressure and temperature. So maybe I have the wrong one down here. Yep, that's it right here. So I've got PV equals nRT, but notice, if you will, that what is happening is I've got two temperatures. That tells you that PV equals nRT can't be used. So I will go with PV over T equals PV over T. Well, now that I have two temperatures, I know they are there, but I'm also given one pressure. So I know that the volumes are not being used. So it's pressure over temperature, which equals pressure over temperature. This is Gay-Lussac's law. So if I plug in my values, I will have 80 over 300 equals new pressure over 250. I simply cross multiply 80 times 250 divided by 300, and I get 66.7 kilopascals. Okay. So now I've got one more equation I need to work with you today, and this one is called Avogadro's law. In Avogadro's law, what we are dealing with is a change in the amount. So you'll notice in the canisters that there were 4 on one side, now there's twice as many on the right side, and that means that you're going to have more space for them. So it's going to increase in volume. So these are directly related to volume. So amount changes the volume. You have to have more space if you have more particles. So that is Avogadro's gas law. And so here's how it works out as a graph. Again, it's a direct relationship. As you increase the number of molecules, particles, gas, you will increase the volume. And we are going to then look at this example problem. So in this example problem, what you will notice, again, PV equals nRT does not work because there are 2 mole values. There's only 1 mole value here. So we will go with PV over, this time, NT equals PV over NT. And what you will see is that I don't have any mention of temperature. It goes away. And I don't have any mention of a pressure. So it goes away. So I have V over T equals V over T. V over N equals V over N. I will substitute in my values. I have 6 liters to start. I have 4.4 moles to start. My volume over here is unknown, but my moles increase to 14.2. How much room will this now have? Cross multiply 6 times 14.2, divide by 4.4, and I get 19.4 is my new volume. This is everything that I wish to share with you. You are a master of the gas laws now. Thank you very much. I will talk with you again very soon. See you. Bye.